In this video, I'll explain what is geometric multiplicity and algebraic multiplicity of an eigenvalue lambda. Geometric multiplicity of an eigenvalue lambda is dimension of eigenspace corresponding to eigenvalue lambda. Eigenspace means it is a collection of all eigenvectors associated with the eigenvalue lambda. We have to find out the dimension of that space, which will give you the geometric multiplicity. That is same as dimension of null space of A minus lambda into I. So algebraically, while finding the geometric multiplicity of eigenvalue lambda, what we are doing is we are finding number of free variables in A minus lambda I into x equal to 0. While solving problems, you will understand how to find out geometric multiplicity. This is the definition of geometric multiplicity. Similarly, algebraic multiplicity of an eigenvalue lambda is number of times it appears as a root of the characteristic polynomial. How many times the root is repeated in the characteristic polynomial, that is called as algebraic multiplicity. And algebraic multiplicity is always greater than or equal to geometric multiplicity. Let us solve few problems to understand the concept. Find geometric multiplicity and algebraic multiplicity of eigenvalues of this matrix. So first let us find out the eigenvalues. So for that we need the characteristic equation of A is, we'll have determinant of A minus lambda I equal to 0. So that gives you determinant of from the diagonal elements you have to subtract lambda. 0 minus lambda, rest all elements same. 1 1 minus lambda, 1 1, 0 0 minus lambda, 0, then 1 1 1 1 minus lambda. This is equal to 0. Now evaluate this determinant along the first, expand this determinant along the first row. So delete first row, first column. You'll get minus lambda into the remaining determinant 1 minus lambda 1 1. Delete first row, first column. Then 0 minus lambda 0. Then 1 1 and 1 minus lambda, which is equal to 0. I have to evaluate this. I'll write here. So this goes here. Minus lambda into, so delete first row, first column. 1 minus lambda into, then minus lambda into 1 minus lambda. Next 0 into 1, it is 0. Then when you have the second element minus 1 into this determinant, it is 0. Therefore, I will not write that term. Plus 1 into last. Delete the first row, third column. 0 minus of minus plus lambda, which is equal to 0. So minus lambda, let us simplify this. So this gives you 1 minus lambda into 1 minus lambda whole square plus lambda, which is equal to 0. So minus lambda into, you can have lambda equal to 0, but you can take lambda common here, lambda square, then 1 minus lambda whole square with a minus sign, then plus 1, which is equal to 0. Then here minus lambda square into minus 1 a minus b whole square formula, minus lambda square because there is a minus outside, minus of minus plus 2 lambda plus 1 equal to 0. Minus 1 plus 1 cancels. Once again lambda can be taken outside. Therefore we will get lambda minus lambda cube into, here minus lambda plus 2 is equal to 0. This implies lambda equal to 0, cubic polynomial here. Therefore lambda equal to 0 is one of the root repeated 3 times, and in this case lambda equal to 2. Therefore totally it is a biquadratic equation. Here it is biquadratic because 4 by 4 matrix, 4 roots must be there. These are the 3 roots, 0 repeated thrice, and this is one more root, lambda equal to 2. Therefore we have total 4 eigenvalues, where 0 is one of the eigenvalue and 2 is another eigenvalue. Therefore algebraic multiplicity means how many times the root is or eigenvalue is repeated in the characteristic equation as a root. So algebraic multiplicity of 0 is equal to, it is 3, because it is repeated 3 times as an eigenvalue in the characteristic equation. Next, algebraic multiplicity of 2 is equal to 1. It is repeated only once. So this is how we find algebraic multiplicity. Now, geometric multiplicity of 0 is dimension of the eigenspace associated with the eigenvalue 0, that is E0, which is equal to number of free variables in a minus 0 into I into x equal to 0, that is null space of this system. So let us do that. How many variables we have, how many free variables we have to find out. So a minus 0 I into x is equal to 0 implies it is ax equal to 0. I'll write the matrix A, and x is a vector with the 4 coordinates x1, x2, x3, x4, which is equal to 0. Now, to find the number of free variables, you should convert this matrix to row reduced echelon form, because we know that any system, if you have a system ax equal to 0 and a dash x equal to 0, where a dash is the row reduced echelon form or row echelon form of the given matrix A, these two systems are always equivalent, means they have the same solutions. So if the matrix is not in the reduced echelon form, we shall reduce it to the echelon form to find the number of free variables. So here 1 1 1 1, then I will apply the operation, only one operation enough here. R4 changes to R4 minus R2. So 0 0 0 0, and this is 1 1 1 1, then 0 0 0 0, then 1 minus 1 0 0 0 0. Then, as in the row echelon form, all 0 rows should be at the end. So R1 interchanged with R2, so that this comes first, rest all 0 rows below the non-zero row. So it is in the reduced row echelon form. Number of free variables means how to count the free variables. See, the first row, first column has a pivot. Next, any of the rows do not have any pivot. Therefore, here the system becomes x1, x2, x3, x4, which is equal to 0. This column corresponds to the variable x1, this to the variable x2, x3, x4. Therefore, only first column has a pivot. If any column do not have any pivot, then that is called as a free variable. X2 is a free variable, x3 is a free variable, x4 is a free variable, as there are no pivots in second, third and fourth rows. Therefore, number of free variables equal to 3. Therefore, geometric multiplicity of 0 is equal to 3. In this case, algebraic multiplicity equal to geometric multiplicity. Next, similarly, we have to find out geometric multiplicity of another eigenvalue, which is 2, is equal to dimension of E2, eigenspace associated with the eigenvalue 2, which is number of free variables in a minus 2I into x equal to 0. Therefore, a minus 2I into x equal to 0. Let us write this first, a minus 2I. From the matrix A, you have to subtract 2I. So from the diagonal elements, you subtract 2. Rest all remain same. So minus 2, 0, 0, 0. 1, 1 minus 2 is minus 1, 1, 1. Then 0, 0, minus 2, 0. 1, 1, 1. 1 minus 2 is minus 1 into x1, x2, x3, x4, which is equal to 0. Now, this is not in the row reduced echelon form. You have to convert to count the number of free variables. We shall do that first. So now, let us reduce it to the row echelon form. Minus 2, 0, 0, 0. 1 minus 1, 1, 1. 0, 0, minus 2, 0. 1, 1, 1, minus 1. So, I will apply the operation R1 interchanged with R2. 1 minus 1, 1, 1. So, that first non-zero entry is 1. Minus 2, 0, 0, 0. Then 0, 0, minus 2, 0. 1, 1, 1 minus 1. Next, I will apply the operation. R4 changes to R4 minus R1. Then R2 changes to R2 plus 2 into R1. So this becomes 1 minus 1, 1, 1. Minus 2 plus 2, it is 0. Then it is R2 plus 2 into R1. So minus 2, then it is 2, 2, then I have 0, 0, minus 2, 0, then 1 minus 1, 0, 1 minus of minus plus it is 2, R4 changes to R2, 4 minus R1, then 1 minus 1 is 0, minus 1, minus 1, minus 2. So 1 minus 1, 0, 1 minus of minus plus 1, that is 1 plus 1, 2, 1 minus 1, 0, minus 1, minus 1, minus 2. Now again, here to make these entries 0, that is R4 changes to R4 plus R2, 1 minus 1, 1, 1, 0 minus 2, 2, 2, 0, 0 minus 2, 0, then 0, 2 minus 2, 0, 0 plus 2, 2, then minus 2 plus 2, again it is 0. So one more is making this 0, that is you will get here R4 changes to R4 plus R3. So 1 minus 1, 1, 1, 0 minus 2, 2, 2, then 0, 0 minus 2, 2, 0, then 0, 0, 0, 0. Okay. Now it is in the row echelon form. You can still convert it into row reduced echelon form. Anyway, I want just the number of free variables. There is a pivot in first column, there is a pivot in the second column, there is a pivot in the third column. For pivot means first non-zero entry, which is to the right of the first non-zero entry of previous row. There is no pivot in the fourth column. This is corresponding to x1, x2, x3. Therefore, x4 is a free variable. Therefore, number of free variables is equal to only 1, equal to 1. Hence, geometric multiplicity of eigenvalue 2 is equal to 1. So, in this example, algebraic multiplicity equal to geometric multiplicity of each eigenvalue. This is how we find the algebraic multiplicity and geometric multiplicity of eigenvalues. Now one more problem. Find geometric multiplicity and algebraic multiplicity of eigenvalues of this matrix. First let us find out eigenvalues. For that we need characteristic equation of A. Determinant of A minus lambda I equal to 0. For a 3 by 3 matrix, characteristic equation is directly given by lambda cube minus trace of A into lambda square plus cofactors of diagonal elements into lambda minus determinant of A equal to 0. So let us find out one by one. Trace of A is sum of diagonal elements 1 plus 1 plus 1, which is 3. Determinant of A equal to 1 into 1 minus 0, which is just 1. Now the cofactors of diagonal elements, delete first row first column, you will get this determinant. Evaluate this. 1 into 1, 1, and sign of each diagonal element is positive, so it is just 1. A22 means delete second row second column, then 1001, value of that determinant is 1, therefore you will get A22 equal to 1. Then delete third row third column, this determinant value is 1, and sign of minor of A33, that is the element in the third row third column, then multiply it with the sign of that element A33, which is nothing but positive. Hence cofactor A33 is equal to plus 1. So when you add all these, you will get 3. So substitute here lambda cube minus 3 lambda square plus 3 lambda minus 1 equal to 0, which is nothing but lambda minus 1 whole cube equal to 0, which implies lambda equal to 1. Solution of this equation is 1, but repeated 3 times because it is a cubic equation. Hence, algebraic multiplicity of eigenvalue 1 is 3, because number of times it is repeated in the characteristic equation as a root. So, which is equal to 3. Now to find out geometric multiplicity of eigenvalue 1, there is only one eigenvalue, which is dimension of the eigenspace associated with the eigenvalue 1, that is dimension of E1. this equal to number of free variables in a minus lambda into I. Lambda is 1, a minus 1 into I equal into x equal to 0. You have to find out number of free variables. So to find number of free variables, a minus 1 into I, that is a minus I, should be in the row reduced echelon form or row echelon form. Now a minus I gives you, from the diagonal elements subtract 1, 0, 0, 0, 1, 0, 1, then 0, 0, 0. This is your a minus I. Into x I had taken x1, x2, x3 because it is a 3 by 3 matrix. Now to write it in the row echelon form, what we should do is just interchange first row and second row. You will get 1, 0, 1, 0, 0, 0, 0, 0, 0. Now you have to count the number of free variables. How to count number of free variables? There is a pivot in the first column. There is no pivot in the second column and third column. This refers to x2, x3. This is your x1. Hence, number of free variables is equal to 2. Where there is no pivot, that is counted as a free variable. There is no pivot in the second column. There is no pivot in the third column. Pivot means first non-zero entry of that row. Okay, there is pivot in the first column, so this can't be the free variable. X1 is not a free variable, it is dependent variable. X2, x3 are free variables, so number of free variables equal to 2. Hence geometric multiplicity of eigenvalue 1 is 2. So in this case, algebraic multiplicity and geometric multiplicity are different, and this relation is always true. Algebraic multiplicity is always greater than or equal to geometric multiplicity.